I would like to talk about behavioral modeling. Now we can even go to a higher level of description in Verilog. Now Verilog was actually meant for building hardware, okay, very quickly, all right, using actually prototypes. And we don't really want to go to the gate level anymore. We want actually to go to a higher level of abstraction. So we can even describe, okay, our hardware, we can describe it algorithmically, okay, using like sequential statements, like we describe it in software. Walid, تفضل. Yes.
Yeah, doctor. Actually, I used it to solve the Verilog 2. So I used this method. And I
Well,
noticed that
so
I
far,
don't have to use it because you asked for continuous assignment in the question.
yeah, you have to be careful. You see that when I tell you to use continuous assignment, you have to use continuous assignment. When I
Yeah.
tell you to use procedural, you use procedural. So it depends, of course, on the assignment, because I really would like you to understand all of these. Okay, how
Yeah,
you
yeah.
can model them different ways. So, for example, in the part one, I ask you to use continuous assignment to model just one BCD adder. In part two, I actually ask you to use module instantiation to instantiate 4 copies of this BCD adder. And then you write actually the test bench, and then you can instantiate the 16-bit BCD adder that you would like to test. Anyways, I will post the solution, inshallah, soon. Okay, but I'm just waiting for all students to finish submitting their assignment number 2, and you will see the solution. The solution is really simple. It's not really that difficult at all. I know it took you some time to understand this, but this was the purpose of this assignment, is to really make you to understand things. Right. Let us talk about behavioral now modeling. Now, so far, we have seen 2 types of procedural blocks. These are the only 2. We have initial and we have always. So we have the initial block and we have the always block, and we use them in test benches. The difference between initial and always is that the case of initial, we execute the enclosed statements only one time. In the case of always, we execute the enclosed statements repeatedly until the simulation terminates. So this is what we have done inside test benches. Now, the body, the statements that are written inside initial and inside the always blocks are called procedural. This is very important. So these are procedural statements. Okay, so you have to use procedural statements inside the initial and inside always. And if you would like to write multiple statements, then you have to enclose them. You have to surround them by begin and end. So when you have a block of statements, you surround them by begin and end. And you can, of course, use more than one always block, okay? Or you can mix between initial and always. Here's an example. Now, for example, this can be used as a test bench. You can use initial to initialize, let us say, the clock here to 0. You can initialize A to a certain 16-bit hexadecimal value. And at some point in time, let us say after 200 nanoseconds, you would like to terminate execution. So this finish here will be like a function. You are calling a function inside the simulator to terminate simulation. We are using 2 always blocks, okay? One here, so every 10 nanoseconds, you would like to invert the clock. So clock becomes not clock. So it becomes, so you start at 0, after 10 nanoseconds, it becomes 1. Then after another 10 nanoseconds at equal to 20, it goes back to 0 and so on. So 0, 1, 0, 1, 0, 1. It changes every 10 nanoseconds. We can do this to model to generate a clock. Okay, I'll talk about clocks when I talk about sequential circuits. I'll come back to this. This is a very important topic. And suppose that I would like now to generate, okay, test values. Okay, for example, for A, I start at this hexadecimal value for A, but every 20 nanoseconds, I would like to increment the value of A. So A becomes A plus 1, which change the value of A every 20 nanoseconds. So this is useful actually in test benches. Okay, one would like to generate test cases. So that's an example about initial and always. Now, what I really would like to show you now is I'm going to show you a different way of using the always statement or the always block, and also procedural statements. So always is not really meant to only generate test cases. It can be used in design. So we can use the always block for designing circuits in Verilog. But now we need to have something, we need to have a sensitivity list. So the syntax of always is like this. You write the always keyword, followed by a sensitivity list, which is enclosed between parentheses. This is my sensitivity list. Notice the at. This is actually part of the syntax. And the sensitivity list is just a list of signals like this. So you can write here at, and between parentheses, you can write signal 1, comma, signal 2, etc. You can actually have any number of signals which are surrounded by parentheses. So they are enclosed inside parentheses. And then you have begin, and then you have end, and inside you have procedural statements. Now, this is how this is the always statement, which is meant to model circuits. So we are describing a circuit now with always. We are not just using for test benches. No, we are using it in design, for designing circuits and for describing these circuits. So the meaning of this always is that we call this sensitivity list because this sensitivity list is going to trigger the execution of the always block. So if there is any change, let us say in signal 1 or in signal 2, anytime there is a change in the value of the signal, yani it was 0, it became 1, or it was 1, it became 0. So we have an event. So we have a change in the value in one of these signals. Then this is going to trigger the execution of the always block. So all of these procedural statements, which are surrounded by begin and they are executed sequentially until we reach the end. So we execute them sequentially and then we stop at the end. Then the always statement is going to wait for another change in one of these signals. So basically the always statement is waiting. Anytime there is a change in one of these signals, which are in the sensitivity list, then this is going to trigger the execution of the always block. Okay, that's the meaning of always. It's very useful, it's very powerful, and we can use it to model, okay, in fact, any circuit in Verilog. And we can describe these, so these procedural statements can be like an if statement, a case statement. We can even write loops. So we can describe the circuit algorithmically, like we are describing software, but we are describing hardware. Now, some of these statements can be synthesized, and the compiler actually can know, okay, what is the circuit that you mean by these statements. Some of them are not synthesizable, okay? So we have to be careful about the use of these statements. Right, so I talked about the sensitivity list. Okay, if you would like to design a combinational circuit, okay, using the always, you must include all the signals. Okay, all the signals here that are read, not written. Okay, they are read inside the always block. For example, okay, I would like to describe here, okay, a circuit that has inputs A, B, and select. So here are my inputs A, B, and select. So these appear in the sensitivity list. Okay, notice the syntax. Now, if select equal to 0, then Z here is my output. It's not an input. So Z becomes A. Now, this is called procedural assignment. It's not continuous. It is procedural because it's done inside the always. Else Z becomes B. Okay. Now, can you tell me what are we trying to describe here with this if-else statement? What does it describe? Do you understand this description? You can figure out what is the circuit that we are trying to describe with this if-else statement. If select equal to 0. Multiplexer. Exactly, it is a multiplexer. So if select equal to 0, then the output, yeah, so if select equal to 0, then we select Z becomes A, else Z becomes B. We're describing a multiplexer using this if-else statement, but this is described, okay, using a procedural statement. So what I mean here by procedural, it's like a statement that you write in a high-level description language. Yani, for example, a statement that you write in Java or C or C++, or C, you name it, okay? So all of these languages are procedural, okay, because they execute the statements one at a time. Yani you finish one statement, you move to the next one, and so on. So basically, you are describing it algorithmically, okay? You can write, of course, many statements here inside, but we only need actually one if-else statement to describe a multiplexer. So this is a simple description, okay, in Verilog. Now notice that here my sensitivity list, it has A, B, and select. These are the inputs. Notice that here we are reading select, we are reading A, we are reading B. So they must appear because this is combinational circuit. These are the inputs. Okay, so therefore they must appear in the sensitivity list. Okay, if you forget to list one of them, then this will change the meaning of the circuit. Okay, so we have to be very careful about it. Is that you have to list all the input signals inside the between parentheses in the sensitivity list. Now, Verilog makes it easier for you because you don't really want to forget, okay, one of the inputs. So if you are describing combinational logic, use @ star. That would be a lot simpler. Okay, so you can write it like this or @ star without even parentheses. Just write @ star here. So if you write here @ star, okay, if you just write it like this, the compiler will understand that this star are the inputs A, B, and select, because you are actually using them inside the always block. So the compiler will replace the star with A, B, and select. So rather than you, okay, describing writing all of this long sensitivity list, if you have, let us say, many inputs, let the compiler to do it for you and just write @ star. So @ star, okay, means that automatically the compiler will actually look at all the signals that are read inside the always block, and it's going to list them, okay, inside between parentheses. But this can be done automatically by the compiler if you write @ star. This is actually how easy it is in Verilog. Now, I said that the statements that you can write here, okay, are procedural statements. So what are these procedural statements? There are many procedural statements in Verilog. You can start with a procedural assignment. You can have an if statement, a case statement. So there are many. Okay, you can even write loops if you want. Okay, all of these are provided as procedural statements, like you have statements in a high-level programming language. The if statement is procedural. The syntax is very similar to high-level programming languages. So you write if, expression between parentheses, you have statement. So if the expression is true, you execute this statement. Else, you have another statement. That's when the expression is false. And the else part is optional. You may or may not have an else part. And if you would like to have more than one statement after if or after else, you surround them by begin and end. So this is called compound statement. That's the meaning of compound statement. You can write many statements, okay? And you can actually have them nested. You can actually have an if statement nested inside another if statement, or we can have nested under else, exactly the same way that you have studied in high-level programming languages. So there is nothing new about it. Let us see how we can model a 2x1 multiplexer. So I would like to have a module now, MUX2. Already we have done this before using, remember, the conditional operator, but I'm going to show it to you differently. See that we have different flavors, different ways of doing the same thing. So I have here a module which is called MUX2. It has a parameter which is n. It has a default value which is 1. Again, this is optional. You may or may not really have this 1 as an optional default value. A and B are bit vectors, n minus 1 down to 0. So these actually are n bits. This is my input A, this is my input B. Notice that these actually are n bit vectors. There is one input here, 1 bit for select. And the output Z here is also a bit vector. It's n minus 1 down to 0, and it's an output. Now here, just to make it actually very clear to you that this always has a sensitivity list. So A, B, and select, these are the inputs. They appear in the sensitivity list. So if select equal to 0, we are selecting Z becomes A, else, it means that select equal to 1, that Z becomes B. So we are describing the multiplexer with an if-else statement. Okay, so that's here my complete module. It is parametric. We're using the parameter n, okay, to describe it. And when you instantiate it, you can specify what is the value of n. And the default value is 1. Now, there is one thing that you should really be careful about it, is that when you write to Z here, okay, when this assignment here is procedural. So let me write here procedural, okay? So what does it mean? Now, it means that if you would like to reassign a different value here for Z inside, you can change it, okay, like a variable. So you can actually change the value of Z many times, okay, inside. If you are writing an algorithm, okay, and you would like to change the value of Z, you can. So because you are using procedural assignment, then this Z here is no longer, okay, it has to be of type register. It has to be of type register. So even though this Z here is the output of this multiplexer, you must be careful about it because you are using Z, you are assigning to it inside the always block. Then this Z must be of type register. Okay, if you don't write register, it will be wire and it will give you a syntax error. So the compiler will detect it. So you have to be very careful about this. Okay, so anytime you are using a procedural assignment to assign to the output here Z, now the output Z is now a variable, not a wire anymore. And for this reason, you have to indicate this, that this is a register. If you don't write register here, it will indicate that this is wire. Okay, but we are using a register. Now, this is not the same thing as a register in a sequential circuit. I'll talk about registers later in great details as memory elements. But this is not the same thing. Here, register means that a variable, okay, in Verilog, and you can use it in a procedural assignment. So you must here use, okay, register. You cannot omit the keyword register in the output because we are using procedural assignment to assign to the output Z. So be very careful about this, okay? So that's one example about how we can model a 2x1 multiplexer. Another example, let us say I would like to model a 3x8 decoder. Okay, that will be interesting. A decoder now is a 3x8, so there is no parameter here. Okay, so the input A consists of 3 bits, 2 down to 0, and the output here D consists of 8 bits. Notice that it's of type register because I'm using here procedural assignment was assigned to D. I'm using nested if-else statements. If A equal to 0, then D becomes this output. So notice that here that bit 0 will be equal to 1. If A is equal to 1, then bit 1 will be equal to 1. All the remaining bits are all 0. So I'm describing this as 8 bits in binary. Okay, 2, then this is actually bit 2. 3, this is bit 3, and so on. So we go here from 0 all the way here to 6. This final else, it means 7. This will be actually bit 7. Okay, so one of the outputs is equal to 1. All the remaining outputs are zeros. This is a decoder, right? That's actually what the decoder does. It's going to output, okay, one of the outputs will be equal to 1, and all the remaining outputs are zeros. Now notice that here I'm using D, I'm showing D in binary. I'm using here the base is binary, whereas A, I'm using it in decimal. A equal to 2, A equal to 3, 4. This is decimal. So even though it's actually a bit factor here, 2 down to 0, it can go from 0 to 7. You can actually use here decimal values to represent the value of A. Not only binary, but also you can actually also use decimal values. So you can write it in binary, you can write it in decimal. You have the choice. Here's another example. Okay, I'm going to show to you how we can model a 4x2 priority encoder. Remember priority encoder? Okay, it's an encoder, but we give priorities to its inputs. So my input here is D, 4 down to 0. Okay, sorry, 4, yeah, so 4 down to 0. So this actually is a 4-bit input D. I have two outputs. I have here V, that indicates whether the output is valid or not. And I have here the output A, which is only 2 bits, that will encode that which input is a 1. Okay, Again, I'm writing this as an always statement. The only input here is D. It is shown in the sensitivity list. Now here, if D3 is equal to 1, then in this case, A will be equal to 1, 1, and V will be equal to 1. So notice that how I'm assigning to my both outputs in the same statement, in one procedural statement. So this V becomes 1, and this A becomes 1, 1. So notice that I'm encoding. So if D3 here, it means that if D3 equal 1, that's what it means. You can write it also this way. Okay, so that actually is cool. Okay, you can do something like this. You can assign to V and A in one procedural assignment. You don't really have to write two, and you can use the concatenation operator. That's actually really something which is really good. Now this else here, it means that if D3 equal to 0, okay, then in this case we check D2. So we are giving the highest priority to D3, then D2. So we go to the else if D3 equal to 0, then we check D2. So this is why here the input 3 has the highest priority and the input 0 has the lowest priority. So it's a 4x2 priority encoder. You can see that here the D input consists of 4 bits. This is actually D. Okay, 3 down to 0. So this is my D input. Now notice that I have two outputs. I have V. V indicates that the output is valid or not. So we use V in the case of a priority encoder that will indicate the validity of the output. And also we have the output A that will encode that which input is a 1. But in the case of priority encoder, you can have more than one input as a 1 at the same time. So therefore, we have to give priorities to these inputs. So in this priority encoder, in this example, I'm giving input D3 the highest priority. So if D3, it means that if D3 equal to 1, then we get the output equal to 1, 1. Okay, so A becomes 1, 1. And V here becomes 1. You can see that this is actually the value of V, and this is the value of A. So this is V, and this is A. Okay. So we are doing two assignments in one. Notice that I'm using here the concatenation operator to concatenate V with A. So we are assigning 1 bit to V and 2 bits to A. And we are doing these two assignments in one using the concatenation operator. So this is very useful and very powerful in Verilog, is that you can assign to more than one output at the same time. Notice that this assignment is procedural. It's not continuous assignment. This is a procedural assignment, which is done inside the always statement. And because it is procedural, then the outputs V and A must be of type register. So this is why we have to use the keyword register in the output. So you have to be very careful about this, because if you omit the register, then you cannot do this assignment. You cannot assign to V and A. You cannot really use procedural assignment if the output is not of type register. So for this reason, it must be of type register. So we have to use the register keyword anytime we use a procedural assignment. Okay. Now this is if D3 equal to 1. If D3 equal to 0, we reach to the else part. So else here means that D3 is not equal to 0. So it's not equal to 1. It must be equal to 0. We check D2. So here, if D2 equal to 1, yani D3 equal to 0 and D2 equal to 1, then the output A will be 1, 0. And it is also valid. Else, it means that D3, D2 are both 0, 0, and D1 equal to 1. Then we get 0, 1. That indicates output 1. Else, it means that here D3, D2, D1 are 0, 0, 0, and D0 is equal to 1. That's here else if D0. You get the output is 0, 0, and it is valid. So 0, 0 here encodes, okay, which input is equal to a 1. And finally, I have this final else. This final else is reached if all the inputs are all zeros. So if all the inputs are zeros, then in this case, the output will be invalid. So notice that V here is equal to 0, indicating that the output is invalid. So this is the meaning of the V bit. We need this to distinguish, okay, if the input V0 is equal to 1 or all the inputs are zeros. So for this reason, we have this extra output, which is V. So this is what we do. This is how we model a 4x2 priority encoder. So naturally, because we are using an if-else and we are using nested if-else, so always we give priority to the if before the else if. And this is why we are writing D3 on top, because it has the highest priority. And then we have else if D2 because it has the second highest priority, and so on. So so the use of the if statement, okay, or the nested if else statement describes the priority encoder. Okay, so this is how we describe priority encoder in Verilog. Do you have any question about this? طيب. I do have another example about how we model a magnitude comparator. So the magnitude comparator has two inputs, A and B. Notice that these are n-bit vectors. I'm using a parameter n. So this is a parametric description. You can change the value of n when you instantiate this comparator. So these are my inputs here, A and B, and these are n-bit inputs. And it has three outputs, greater than, equal, and less than. So these are the outputs of the comparator. Now, all of this is behavioral description. I'm going to use the always statement. Okay, in all these descriptions, I'm going to use the always statement. So this always is sensitive to the inputs A and B. So inside this always statement, we can check if A is greater than B, or A is equal to B, or A is less than B. So we can use the greater than operator to detect if A is greater than B. So if A is greater than B, then GT will be equal to 1. Whereas equal and less than will be equal to 0, 0. So notice that how I'm assigning to three outputs in one assignment, in one procedural assignment. We're assigning three outputs, GT, equal, and less than. GT will be equal to 1, while equal and less than will be 0, 0. Okay, so we are assigning three outputs in the same statement. That can be done using the concatenation operator. So I'm concatenating the three outputs, GT, equal, and less than, and we are doing one procedural assignment to these three outputs. Now, else, it means it's not greater than. If it is equal to B, notice that here equal means equality, then we assign 1 to equal. And this final else, it means it's not greater than, it's not equal, it must be less than. So we assign 1 here to less than. So this is a description of the n-bit magnitude comparator. And notice that this description is a high-level description. It describes the behavior of the comparator. There is no need to write any equations. We can just use the relation operators for doing comparison. If you are using a synthesis tool, then the synthesis tool will understand that this is a comparator because you are comparing the inputs A with B, and therefore it can generate a circuit that does the comparison for you. Already we have designed a circuit that implements this comparator, but there is no need to write actually Boolean expressions here. You can just use the relation operators for describing this comparator. Again, the output here are of type register because we are using here procedural assignment. So this assignment here, you can see this, the assignment operator is procedural. So procedural because we are using this inside always, and this is why the outputs must be of type register. Okay. Now, what we have seen in the previous examples are we have seen if else. Okay, we can also use case statement. And there are many statements in the Verilog hardware description language that you can use for behavioral description, that you can use them inside the body of always. We have seen if else, nested if else. You can also use case. Now, the case statement is also procedural. and you can use it inside always. And the syntax is as shown here. You can write case, between parentheses, you can write an expression. And this is followed by many case items. These are the values, the possible values of the expression. So if the expression, its value matches one of these case items, then we have here the statement. So the statement will be executed, okay, if the expression matches one of these case items. And then we have the default case. Okay, so if a case item is not listed, then the expression, if the expression does not really match any of the case items, then it's going to match the default case. And then we can have a statement here. So this default case is optional. It is used to simplify, okay, so in case if we have, for example, the expression does not really match any of the case items, we use the default case for that purpose. Now, this statement here, you can actually have a single statement or you can have a compound statement. And the compound statement is surrounded by begin and end. And if you would like to have multiple statements after a case item, it is possible as long as you surround them by begin and end. So you have to use this syntax. This is the syntax which is used in Verilog. I have an example. Yes, تفضل.
Doctor,
yes.
The case statement, is it like the switch in software?
It is switch, yes. So it is the switch statement in Java and C. So Java and C calls it the switch statement, but in the case of Verilog, they call it case statement. So the syntax is slightly different, but the meaning is the same. Yes.
Okay, thank you.
Right. So now if I would like to model, let us say a multiplexer, I can model it with a case statement. And rather than using an if, else, if, right, nested if, else statements, I can use the case statement. It will be very simple. So here's an example of a 4x1 multiplexer. It's called MUX4. It uses a parameter which is n. It has 4 data inputs here, A, B, C, D. These are bit vectors, n-1 down to 0. So these are n bits. And we have only 2 bits here for select. You can see there are only 2 wires. So this is actually my select input. It only consists of 2 bits, bit 1 and bit 0. And the output Z here, you can see the output Z, it consists of n bits. So here my output Z is a bit vector. I can describe this multiplexer using an always statement. So this is a behavioral modeling of this multiplexer. Now notice that we have here 5 inputs, A, B, C, D, and select. So you can write all of these between parentheses. This will be the sensitivity list. It means that always is sensitive to these inputs. But since we are describing combinational logic, you can simply write it as at star here. That will be easier. Okay, so this way you don't really forget to write one of the inputs between parentheses. It's actually very easy. So whenever you would like to model a combinational circuit in Verilog, okay, it is recommended that you use at star. First, it makes it actually easier on you to write, and you have to write less. And second, you don't really make any mistake. You don't really forget an input. So this way you avoid making mistakes. The compiler will replace this star with all of these inputs. So all of these inputs will be, automatically the compiler is going to substitute, okay, all of these inputs between parentheses because it sees that these inputs are used inside the always block. So notice that we have here A, B, C, D, here we have select. So all of them appear inside always. So this is why always is sensitive to all of these inputs. Now we can describe the multiplexer with a case. Notice that the expression here is my select input, and we have 4 cases. 0, 0, you have 0, 1, you have 1, 0, and 1, 1. So for 0, 0, you have Z becomes A. For 0, 1, Z becomes B. 1, 0, Z becomes C. You can write also here 1, 1. But rather than writing 1, 1, you can also write the default case. That also will work. And if it does not really match, select is not really 0, 0, 0, 1 or 1, 0, it's going to match default. And Z becomes D. So this is actually one way to use the default case. Okay, so notice that these inputs here are shown, select is shown here in binary, 2 bits in binary. you can also write it in decimal. Yeah, I can write, for example, I can write 0 here. I can write 1. I can write 2. You can also have a default case, or you can write even 3. So you can actually show the value of select. The case item can be shown not only in binary, but you can also show it in decimal if you would like. So whatever actually is convenient for you, you can actually use it in Verilog. Right. So that's actually is okay. This is the case statement, and you can see that the case statement is very useful to model a multiplexer. Let us model a multifunction ALU. Remember the ALU from my previous lecture. Okay, so this is the ALU symbol. You can have here 2 data inputs, A and B. These are bit vectors, each one consisting of n bits, n minus 1 down to 0. And then you can here have the function as an input that will control the ALU. So you would like to specify what should be the function to be executed by the ALU. So here is my module, which is called ALU. It has a parameter n. This n here will specify the number of bits in the inputs A and B. So notice that A and B here are my inputs. These are n-bit vectors, n minus 1 down to 0. The function f consists of only 2 bits, because we only have 4 functions in this simple ALU. This is just a simple ALU. We have the output, which is z, okay, which is n-bit vector. And also we have an additional output, which is c out. Okay, so you can also produce a c out. Now, we write an always statement to describe the behavior of this ALU. So this always, notice that I'm using here at star, because this is combinational. Now, the compiler is going to replace the star with A, B, and F, because all of these are inputs, okay, to the ALU. I'm using a case statement because I would like to look here at the value of F. So we have 4 possible values of F, 0, 0, 0, 1, 1, 0, and 1, 1. So you can list these values here. I'm using a default case in the case of 1, 1. In the case of 0, 0, I would like to calculate A plus B. So this will be addition. So when you add A plus B, you are adding n bits plus n bits. You will get n plus 1 bits. You will get a carry out. So you can produce Z, which is the n-bit output, plus a carry out. So notice that we are concatenating C out with Z, because I would like to assign, okay, the most significant bit here to C out in the case when we have an output carry. So in the case of when the F equal to 0, 0, we do addition. In the case of 0, 1, we do subtraction. So I can write it here as A minus B. So I can use the ALU to do addition and to do subtraction. By the way, you can use the minus operator in Verilog, and this indicates subtraction. Now, you can write it like this, but since we know that subtraction can be converted into addition to the 2's complement, you can also write it like this as A plus, you can write here not B, that will be the 1's complement of B, plus 1. That also can be another way to describe here the output. So rather than writing this, you can actually write this. Now this will be nice. Okay, this will be nice to write as A plus not B plus 1 to indicate that I would like to use the same adder for doing addition and subtraction. So I don't really need to use a different circuit for subtraction. I can use the same adder to do addition and subtraction. Of course, I need inverters to invert B, and I need actually to use the carry 0, the carry in, okay, to add plus 1. Okay, so so this means that here, if there is a synthesis tool, it will actually try to synthesize this using the same adder to do both addition and subtraction. Now you can also define logic operations like A and B, A or B. You can define more functions if you want to. In fact, Verilog assignment number 3 is about modeling a multifunction ALU. So go over this assignment. It's already posted on the Blackboard, and you can do it in groups of 2 students. So really you don't really have to work alone. Yani you can really find a partner, choose your partner, and work on this assignment so that you can finish it quickly and early. You don't really have to leave it until the last day. So it's an interesting assignment. It will teach you a lot about behavioral modeling in Verilog. In fact, it mixes between behavioral modeling and also between module instantiation, yani structural modeling. So you have to do both in this assignment. It's very interesting. So go over it. You can actually learn a lot, okay, by doing these Verilog assignments. So this is how we can model a very simple multifunction ALU. I call it multifunction because it can do addition, it can do subtraction, it can do logic operations. We can control it using the function input, which is called f. F here is the function, okay, of the ALU. And you can produce, in addition to the output Z, you can also produce a carry out. In the assignment, you have to produce carry out. You have to produce, in addition to the output, you have to produce the carry out. You have to detect if there is overflow. You can also produce 2 additional outputs that will indicate if A is less than B or A. So you can actually do it for signed as well as unsigned comparison of A and B. So it's an interesting assignment, and you really need to understand it. It's not really that difficult at all. And you can actually really do it very quickly if you understand. Okay, we have already discussed this actually in previous lectures about how you can, about arithmetic circuits and also about the ALU. So try to go back and see these things, and you can really solve it very easy. Okay, that will be Verilog assignment number 3. Right. So this is about an ALU. My last example today will be about modeling a BCD to 7-segment decoder. Already we have seen the BCD to 7-segment decoder. Remember combinational circuit design, I talked about it at the beginning of the semester. And the input here will be BCD. It is just 4 bits. And the output will be 7 segments. Now here I'm numbering them from 6 down to 0. You can also call them A, B, C, D, E, F, G, but I prefer to use a bit vector. That will be actually a lot easier for me. It can be described with an always statement. It's very easy, and a case statement. So you don't even have to do it the way that we have done it before. Yani you don't even have to use Carnot maps, obtain the equations, try to extract the common sub-expressions, and yani it takes time, okay, with Carnot maps. You don't even have to do it this way. What you can do is that you can describe the behavior of this BCD to 7-segment decoder very easily in Verilog using an always statement without knowing the equations. And if you have really a synthesis tool, the synthesis tool can take this description and generate all the equations and the circuit for you. So this can be automated. That's really the idea of using Verilog. You can use it for 2 purposes. You can actually use it to simulate and to verify the correctness of your circuit. That is one purpose. And there is a second purpose of Verilog, is that you can use it to automate the process of generating a circuit for you. So you can use a high-level description, okay, using behavioral modeling, and then let the synthesis tool, okay, like a special compiler that can translate this description into a circuit. Okay, so we use compilers in software programming languages to translate software into assembly language code and machine code so that we can run the software on the CPU. Now here we are using a compiler to produce a circuit, okay, not software. That's the major difference. Hamna?
Yes, doctor. These tools always, or in general, like produce the most efficient circuits, or?
Yeah, well, there are, you see that people have been actually designing these tools for decades. Yani if you go back to Verilog, it was introduced like more than 30 years ago, and people actually tried to refine these tools and improve them and to actually to optimize them. Of course, these like compilers, okay, some compilers actually can generate actually faster code. The same thing here, okay, so you can actually use a tool that can generate actually a more optimal circuit. It tries to optimize this. It depends on the tool itself, okay, the capability of this tool, how far actually it can produce optimal circuits. Yes. So people actually spend their career designing such tools, and they give it to people. I mean, there are actually companies that can produce these tools so that it will make the task of the engineer easier, so that you can describe things at a high level. You can describe something which is very complex. You can describe it with ease, okay, in Verilog, and let the tool to generate. Because when you are dealing actually with really large circuits, when you would like to design a CPU, you are not dealing with 10 gates or 20 gates, not even thousands, maybe millions, okay? Then in this case, you cannot actually do it manually by hand. You cannot really produce all of these equations by hand. You need tools that will automate this process, okay? And some tools are better than other tools, of course. Right. So in this example is very simple. All what I need to do, I would like to produce the 7-segment output based on my BCD input. So notice that my always is sensitive. There is only one input, which is BCD. So notice that this is my sensitivity list. You can write it as at star, or you can write it as at BCD. In fact, BCD here is a 4-bit vector. So this is not really one input. These actually are 4 bits. And then we are writing a case statement. So case here, because we have all of these cases here for BCD. Now notice that I'm not describing here the case items in binary. I'm describing them in decimal. You have a choice. And in Verilog, you can describe the values of BCD. You can describe them in, and if you have an integer, you can actually show this integer value in binary. You can also show it in decimal. You can show it in hexadecimal. You have actually different ways of writing the same number. So here we are writing them as 0, 1, 2, 3, and so on, right? Up to 9. And then we show the output. So here you can see here the 7-segment output. So this is here actually segment. This is my output segment. These actually are 7 segments. I'm showing them in binary. I'm showing them actually 7 bits in binary for clarity. So I really would like to show that each segment, for example, this will be segment A, this will be segment B, this will be C, this will be D, this is E, F, and G. And in the case of 0, we turn on 6 segments from A to F, and we turn off G. So this will display 0. If you would like to display 1, then basically you have to make B and C are equal to 1 and 1, and the rest are zeros, and so on. So all what you have to do is just to indicate that which segments are on and which ones are off, and that's it. So we're describing it from 0 to 9, and I'm actually using here a bit vector here, 6 down to 0. You can call it 6 down to 0, or you can call it from 1 to 7. This is better than actually listing them as A, B. You can also write it like A, B, C, all the way here to G. But I prefer to use a bit vector. That will be a lot simpler for me to express it, okay, in Verilog. So using a bit vector rather than names. This is just a matter of naming, okay, the outputs. Notice that this assignment is procedural. You have to use register here, so don't forget about this. Finally, there is a default case. Okay, so this default case is very important because the input BCD, it is supposed to be BCD from 0 to 9, but you might actually get an input which is not BCD, from 10 to 15. So if you have your BCD input is from 10 to 15, then you would like to turn off all these 7 segments. You don't really want to display anything. So in case you have a wrong input, okay, which is not BCD, you would like to turn off all these 7 segments. So this is why the default case is very important. You should not really forget about it. Okay, so this is a description here of the BCD to 7 segment display. Now, typically you will write each one of these on a separate line. So these will appear on separate lines, but really I don't really have the space to fit all of this description on the same slide. So this is why I'm writing here 2 case items on the same line, but really typically you will write each one on a separate line, okay, to make it more readable, okay, that when you would like to type this Verilog description. Do you have any question about this? So I did not really use any equations at all, okay? We rely on the tool to generate the equations for us. So this is what we call here behavioral description, okay?